Hi everyone, I'm Brenner Heintz from Confluent. Here's a challenge that every enterprise faces. Your operational databases are just constantly changing. You've got new orders placed, inventory that's updated on a just continuous basis. Customer records get modified when someone moves or changes their name. But your analytics, your dashboards, your machine learning models, are those changing as frequently as your data is? Chances are it's not. Today, I'll show you how change data capture with the power of Debezium and Kafka eliminates that gap entirely. So let's dive in and see this in action. All right, so here we are in the Confluent workspace, looking at the Postgres Debezium connector. As you can see, it's been very busy. We have over 8 million messages processed in the last 7 days. A couple of things to point out here. The first is that for all of the tables that we pull in with this connector, they're automatically added to Schema registry, and we can add a specific topic prefix here. In this case, it's the changes topic prefix. We also can choose whether we want to see the after state only or both the before and the after state for all of our tables. In this case, we're going to include both before and after. And then also we have the ability to pull out some of these metadata columns with some specific transforms. All right, so let's go ahead and take a look at one of these tables. Our very first one is the customers table. This is one of the fundamental tables that we have here that we're going to build our data products upon. As you can see, it's got pretty basic info. Just customer names, billing address IDs that reference a customer or an address's table. And we've added those additional op and deleted metadata columns on the end there. The op column refers to what sort of operation has been performed on our table if a record has been added or modified. R stands for read, but the other operations are create, insert, and update. Those are the ones where we'll see when we make changes to our database or we insert new records. R refers to when a table is first read, an initial read. So here's that second table I was telling you about, the addresses table. We've stored customers' addresses in records A1 through 80 here, and we have address information along with those two additional metadata columns. We're going to combine this addresses table with the customers table to create our first data product a little bit later, the enriched customers data product. But for now, I want to show you what change data capture actually looks like here. So I've created a basic Python script with some of the legends of rock from the 70s and 80s, rockers that you can see on screen here, like Sting, Bob Dylan, Stevie Nicks. So this script inserts records directly into our operational Postgres database, which is running on AWS. We're going to insert these records directly so you can see how quickly Debezium picks up these new records and replicates them to our tables. So as you're seeing here, on top in our workspace, we can see the current state of our tables up top. Down below, however, we're with the Confluent Flink shell viewing the change log. And in the very left-hand column, you see the operation type. Here we have a ton of updates and inserts and one delete so far. We're deleting records of rockers that have passed away after we insert them. So what you're seeing here is those records updating in real time as the script inserts, updates, and deletes the records from our operational database. All those changes are being streamed in real time. You'll notice that when a record gets deleted, it no longer shows up in the screen on top that shows the current state of the table. That's because if it was deleted, we don't want it in our records anymore. But you can change this if you like to use that to do soft deletes with that deleted flag. Finally, another thing you probably noticed is that in the operation column, there's pluses or minus associated with each update, delete, etc. That's because the Postgres database is submitting full changes for each update, and insert, or delete. That includes a before and after state for each event. The before event is designated with a minus sign, while the after state event is designated with a plus. That's why for updates you see 2 rows, and for inserts you only see 1, because inserts don't have a before state. So this detailed changelog makes for unparalleled auditability, reproducibility, and replayability of our data after the fact. And this is really important for highly regulated industries. Taking a look at specific records here from that changelog, we could see we had an operation of create there. And of course, if we refresh the table in the operational database through dbeaver here, we can see all of those rockers are now present in our database. All right, jumping back into the workspace here, we'll take a look at the schema by running this describe extended command of our customers table. As you can see, customer ID is the primary key. We've added a rockstar column earlier. By default, we made that true for all of our new rockers. And we have those new metadata columns as well. Let's now actually do some schema evolution. We're going to add a column to indicate whether each of those rockers and our original customers are deceased. We hope they're not. So what we've done is we've actually added a new record as well. We've added Jimi Hendrix as record 217 so that that schema change is actually reflected in our tables. If we just make that change without adding any new customers that have that new column, it won't be reflected yet because Postgres won't emit that change. So diving into the customers sidebar here, it has details about the schema that we can just view at a glance here. We know we've got those first two metadata columns, so we jump right to the third to last column, and sure enough, our new deceased column is reflected in the table, in the schema of the table. However, if we go back a version here to version 5, we're on version 6, no such column exists. There are our two metadata columns there, but the most recent column that was added was a rockstar column. So as you can see, not only does Debezium, when pulling in those new tables, automatically add them to schema registry, it also automatically evolves the schema as the schema changes over time. So this is super, super valuable, as you can imagine. It means there's no manual intervention here needed when your data changes, when the shape of it changes, and of course, as any data engineer knows, it inevitably does. All right, jumping back to our workspace again here. Double-clicking into the topic here and opening the most recent message, you'll notice that in this version of our customers table that we've been working on so far, when we open the Kafka, individual Kafka messages themselves, we just see the data, customer ID, customer name, email, and so on. In this topic, though, I've configured things slightly differently. Here we're pulling in both the before and after state of each record directly into Kafka in the classic Debezium envelope message structure. I'm sure this is probably familiar to you if you've spent much time with Debezium. This envelope structure contains loads of metadata for each row and each new transaction as it streams new messages into Kafka. There's information about our connector, what version of the connector we're using, timestamp information, schema info, all of that you can see here, transaction ID, in addition to info about the operation type and the soft delete flag that's present in our other tables. So I wanted to show you what this looks like because this is the classic Debezium envelope format with all that information for each transaction. But this format can be really hard to work with because all of our actual data columns, the ones that we normally want to get at and do something with, are nested within this envelope, and getting at them is not so easy. Luckily, retaining this, if retaining this information is important to us and we want the highest fidelity metadata possible, then we can import our records in this format and simply convert them using Confluent Cloud native Debezium formats. I'll share a link to the documentation on those. They enable you to transform your data from what you see here to those simple, easy to use data with the columns that we expect, like I showed you in the other customers table that we're working with. All right, so far we've seen change data capture in action. We've seen the Flink changelog with before and after events for updates, inserts, and deletes. And we've peeked under the hood at the raw Debezium envelope format to understand what it looks like and how Confluent Cloud makes working with these formats easier. Now this is where things get really cool. Here we see the enriched customers topic. This is the next step, to actually build something with our replicated Postgres data, our first data product. Let's see what that looks like here. We've combined our customer information. We see some of our rock stars there. We also have other non-rock stars in our data. And we've combined them with their addresses. So for this table, we are going to denormalize and flatten the data so it's easier to work with and represents actual business entities. In this case, we're combining customers and addresses tables so that we can see each customer's shipping and billing addresses on a single line of the table. So this, of course, would be useful, for example, for customer service reps. Obviously, they don't want to go joining these tables together in Postgres every time they need to help a customer. Instead, we can create a flattened table that makes that information really, really easy to find and do analytics on. All right, so here's what the create table statement looks like, the DDL for our enriched customers table. Let's break this down. First, we've got a primary key on customer ID. This is super important. It will handle deduplication for us automatically. Finally, the real-time magic here. Here's what's beautiful about this. Every time something changes in the source tables, a new customer gets added, boom, it's simply there. It appears right in enriched customers. If someone changes their shipping address, it's there. A customer gets deleted, it gets filtered out automatically. It's no longer there. See those row structures for addresses? We're flattening out the address data into nice, unnested objects. The watermark here is telling Flink how to handle late arriving data. Basically, with this 5-second interval, we're saying give events up to 5 seconds to arrive before we consider them late. Next, here's where the magic happens. We're taking our customers table and doing 2 left joins with the addresses table. The reason that we do left joins here is because not every customer might have both a shipping and a billing address set up yet. We don't want to lose those customers being in this table just because they're missing an address, for example. And then finally, see where those where clauses are checking for the deleted flag? That's just us filtering out any soft deleted records. We only, of course, want active live data in our enriched views. And this is not a nightly batch job. This is continuous real-time data enrichment. So we've built an always up-to-date enriched data product that deduplicates based on primary key, filters out deleted records automatically, gives us a single place to query for complete customer information, and updates any source data changes in real time. And here's the kicker. The SQL we just wrote is not that different from what you'd write for a batch process. The complexity isn't in learning some crazy new syntax here. Flink SQL is just like other variations of SQL. It's just a little different because it uses real-time data. All right, so let's build something else on top of our enriched customers table. First, we create this simple intermediate view here, this intermediate table called products with PK. Nothing flashy here, just necessary, simple sort of shift left data transformation. Our products table wasn't properly defined with a primary key at the source, but we need it to be in order to build our next data product, which we'll jump into right after this. So we accomplish this here with the primary key not enforced statement in the middle there. Now here's where it gets really powerful. We are building the ultimate sales data product here. Look at what we're combining here. We're combining orders, order items, products, and that enriched customer table we just created to get a complete 360-degree view of every transaction. The real magic is in these temporal joins here. See the for system time as of clauses? These are huge. So when an order comes in at a specific time, like today at 2 p.m., we then do the join at that moment with those other tables, with product prices, with customer data, with customer addresses, as they existed at 2 p.m., not as they exist right now. So if a price changes or a customer's name or their address changes later, these tables, today's orders, will still show the correct price, the correct name, the correct address from when the customer actually made that purchase. All right, so here's what that table actually looks like. Here's the final result. We've got order time, order ID, product ID, customer name, shipping and billing addresses, and product quantity, along with total transaction amount. This is high fidelity data that absolutely powers our business. And we've taken it out of the operational database, denormalized it, joined, joined it with other tables, and transformed it to create a new data product that we can use for customer service, creating dashboards, or to give our data scientists something to build machine learning models off of. All right, now let's jump back to the product sales topic page. To make this a true data product that's consumable by even more downstream users, applications, microservices, and other entities, and to persist that data in a durable format that's easily queryable by the search engine of your or query engine rather of your choice, like AWS Redshift, Snowflake, Databricks, we can use Tableflow. Tableflow allows us to convert data to Iceberg or Delta Lake format with just the click of a button. Boom, it's that easy. Our data is saved and continuously updated in Iceberg or Delta Lake format, and there's nothing else we need to do. But while we're waiting for that to be ready, let's take a look at the most recent message from product sales. There we go. All right. And here's our final data product. This is where real-time analytics gets really exciting. We're building a rolling 30-day customer activity snapshot that updates continuously. So check out this window function. This part here, range between interval 30-day preceding and current row. Every time a new order comes in, we're automatically recalculating each customer's total spending and order count for their last 30 days of activity. This is not a fixed calendar month. This is their rolling 30-day window. And when an order from 31 days ago falls off of that rolling window, those totals automatically adjust. There's no batch jobs, no overnight recalculations, just a continuous rolling window here. All right, so here, let's take a look at this table. Here we can see the results of the query, and we can use this information to understand who our biggest customers are and what their spending patterns are. And in the lab that accompanies this demo in GitHub, we even show you how to put this information back into your original Postgres database. It's really just a matter of setting up a new Postgres database data sync that's a lot like the Debezium Postgres data source we set up here. Once you drop data into your operational database, it's just a matter of creating the proper tables, and voila. You add this information to your existing records, like adding their 30-day purchase history and totals to your operational database. And that sort of reverse ETL, it can be really, really powerful if done properly. All right. The other way that you could make use of this data is to sync it to places where people want to query it. So let's hop over to Redshift now. I already showed you how easy it is to start using Tableflow with your existing Kafka topics to get that data into Iceberg or Delta Lake format. We did so in Iceberg today. Here we use the Redshift Sync connector to land our continuously changing data in Redshift. So there they are. Both the product sales and the 30-day customer snapshot table are right there, and they're ready to query. So if Redshift's your query engine and editor of choice, this is a really, really easy way to get started querying and analyzing that data based upon the data products we created earlier. All right, so now that we've done some transformations, we've created data products, created temporal tables, and we've moved our data from source to destination, all with that continuous goodness of replication, continuous replication, and real-time data capture. It's nice to be able to take a look at the big picture. Here we're jumping into the stream lineage section of Confluent Cloud. So when you have data flowing in between different topics, using Flink to transform that data, this shows you exactly how and where it's flowing, from Postgres through Debezium into Kafka topics, through Flink transformations and tables, and then finally out into Redshift. That's pretty cool, huh? This can be really useful to visualize all your data flows and make sure they match up with what you're expecting. And you can click into any of these topic nodes here and see what the recent activity's been, like how much data is flowing through your topic over time. It's really cool. All right, thank you for joining. Check out the GitHub repo for this demo on GitHub to try it yourself, or you can even go beyond with what we've had the time to share with you today in Lab 2 of the repo. This was Lab 1. There's an entirely different module that you can take on and learn even more about Flink, change data capture, Debezium, and Kafka with. Finally, please connect with me and many other data engineers and practitioners on the Confluent Community Slack channel. Thanks, and have a great day.